Hello, EECS professors and staff. This is Team ProFinder, Francis, Devesh, and Colin. But unfortunately, Colin is remote today, so he won't be present on this presentation here. Our topic was to explore a facial recognition pipeline that could pick out University of Michigan EECS professors from random images on the internet and identify exactly who they are. The project has a lot of applications, from surveillance and security, such as the way you can unlock your iPhone with your face, to organization and convenience, such as how Facebook can tag people in photos before anybody physically tags them. We used a lot of work for this project, including FaceNet, the actual paper. This paper outlines a neural network that produces a unified facial embedding per unique face. This embedding can be used to identify other pictures of the same person, even if that picture is different or misaligned to the original camera angle. The paper specifies a specific loss algorithm known as triplet loss in order to generate this unified embedding, and we'll specify more about this later in the presentation. Overall, we were just fascinated by how computer vision and machine learning intersect, and we wanted to explore it more. And we thought it was an attractive challenge problem to solve, and that's pretty much why we explored this topic as our project.
In our approach to solving this problem, we first started with using completely untrained models. We tried a variety of different architectures. However, we quickly ran into several problems of resource power and training time, as well as data set size. So eventually we switched to transfer learning, where we used the Inception v3 ResNet model as our base, and then added a single fully connected layer on top to generate the feature embedding. However, once we started training this, we found that our loss wasn't converging, so we, after some investigation, we determined that the reason was we were doing hard triplet selection instead of semi-hard triplet selection. In triplet selection, there are essentially three separate images used to calculate a single rose loss. There is an anchor, a positive, and a negative. The anchor is an image of a class. The positive is an image of the same class, and the negative is an image of the different class. In hard triplet selection, you choose the positive, which is farthest away from the anchor, and the negative, which is closest to the anchor. However, in semi-hard triplet selection, you choose a positive and a negative, which are close together, but the positive is still closer to the anchor than the negative is. This aids in convergence and prevents the feature embedding field from collapsing onto a single point in dimensional space for all images. In our experiments, we had several issues. We had issues with loss convergence, we had issues with false positive over detection, and we also had issues with training time and training resources. We addressed the final issue by switching to transfer learning. We addressed loss convergence by evaluating our triplet selection algorithm and turning it from hard triplet selection to semi-hard triplet selection. And our issue with false positive over detection, we believe, had two root causes. One, not enough training time. We believe that if we trained more, that the discrepancy between true positive and false positive rates for any margin would increase. And the second was model complexity. In our last experiment, we added a second fully connected layer into our transfer learning network and found the true positive and false positive graphs all the way on your left, which had a far greater gap between the true positive and false positive rate despite being trained on less epochs.
Overall, at the end of the project, we realized it wasn't successful in establishing the pipeline, and that was disappointing. But we realized a number of factors actually affected our results, including just the simple size of GPUs that we were using and the size of the input dataset that we actually needed to process in order to get this model to work. Ours was 500,000 images, but the true dataset necessary was 200 million images. In order to train a dataset of that size, you need between 1,000 and 2,000 hours, and given the amount of time that we allocated for this project, we simply didn't have the training time necessary. However, we did realize at the end of the project what was causing a lot of the errors. That was our triplet reassignment and selection problem. After realizing this, we retrained the model and actually experienced some successful convergence. Even though it was minuscule, we realized that over the course of maybe 500 to 1,000 more epochs, this loss would converge into an accurate model that could be used in practice to identify faces. We look forward to further exploring how that project can actually develop, and we appreciated the opportunity to explore this in the first place. Now Colin is going to give you a short example of what our pipeline would have done had our models actually converged and been able to train properly.